So, any questions from any of the things we talked about yesterday? Okay, I will just start by reviewing the very last thing that we did. So, here is some recap. So, this is maybe the most important notion in this whole business. So, what we talked about is this notion of orthogonal projection, and so let me state that discussion that we had as a formal theorem. So, it says the following: suppose I have B an inner product space with dimension of V possibly infinite. So, I do not need to actually assume anything about dimension of V. Okay. So, dimension V could be finite dimensional, could be infinite dimensional also, finite or infinite. But what I am going to require is that the subspace that I choose, so I choose a subspace W of V, that should be finite dimensional. So, let this be a finite dimensional subspace of V. Okay. Now, given this data, then here is what we showed: given any vector V in V. So, here is a picture to keep in mind. Here is the subspace W, origin, some vector V. What we can do is to sort of drop a perpendicular. Okay. So, which means I can find a vector W. So, given V in V, there exists a unique. So, I did not quite say this yesterday, let us prove this now. There exists a unique vector, maybe I did, okay. Okay. So, there exists a unique vector W in W such that the following property, that if I take V minus W, then this is perpendicular to every vector in W. Okay. So, this is a statement that we proved yesterday, and so let me just quickly recall how we proved this. So, we said let us choose an orthonormal basis. So, I will abbreviate it to O and B. We choose an orthonormal basis for the subspace. Okay. We will come back to why such a thing exists using the Gram-Schmidt orthogonalization process. So, we will show existence later, but for the moment just granting that it exists. So, let me call, so suppose I have E1, E2, Ek, right. I have assumed W is finite dimensional. So, there are some finitely many orthonormal vectors which form a basis for W, and once I have this, I can find this element W very easily. Okay. So, how do we define W? You just say, so V is given, you define W as follows: you take the inner product of V, okay, V is a known vector with each EI, summation V EI EI, okay, and this is of course an element of W because it is a linear combination of the EIs. Okay. So, the claim is that this is the W that we seek, this is going to be the vector, that is exactly that orthogonal projection, that perpendicular projection. So, why does this W satisfy the required property? We just have to check what so okay, so let us check that W has the correct property. So, what is the inner product of W with any EI? So, since the right hand side is, you have written W as a linear combination of orthonormal vectors, taking inner product with a given EI will just pick out that coefficient. So, this will just tell me whatever is the coefficient of EI on the right hand side, okay, but that coefficient has been chosen to be VEI. Okay. So, by construction of W, I know that WEI is exactly VEI for all I. In particular, it means if I subtract one from the other, V minus W EI is 0. Okay, now what that means is that V minus W is perpendicular to all the EIs, but since EIs span that space W, they form a basis, it means it is perpendicular to every element x, right, just by you can write any x as a linear combination of the EIs and prove this. So, this was our proof. You have to construct it cleverly, that is more or less the crux of the argument. Okay. Any questions on this?
So, what if W is not finite dimensional?
Right, then we can't say much in general. So, if we are talking about infinite dimensional spaces, both being infinite dimensional, then we can't always say this. So, we need some additional conditions. So, usually the context in which this is done there is you have a what is called a Hilbert space and you have a closed subspace and so on. So, then you can do pretty much the same things. Okay.
This looks like Galerkin method.
Sorry, what?
This looks like Galerkin method they are projecting there.
Sorry, I don't know what that is. What does Galerkin method do?
So the PD when we they solve it,
Like
Fourier series, the coefficient x, sin x, cosine x, they will, that time they will do it. The infinite also it's working. Some compact x argument they will add.
That's what. So you need. So you're saying, can we define this projection in general for infinite dimensions? You can, but you need some more conditions. You need a closed subspace if it's a Hilbert space and so on. So that it will require some convergence, etc. to happen.
Method they call Galerkin method.
I see. Okay. So yeah. So the answer in some sense is yes, you can, with some additional hypothesis on W. Okay. Now. Okay, what's happened to if a new page is somewhere here? Yes, thank you, correct. Okay, so uniqueness, I only showed existence of W by correctly constructing it. How do you show uniqueness? So let's prove this. So see, if I have two such are elements of W, both of it satisfy this condition, both satisfy what we want, that V minus W is perpendicular to all x, V minus W prime is also perpendicular to all x, okay, this is for all x in W. Then what it means in particular is, if I subtract one from the other, okay, this means, so let me subtract. So V minus W minus V minus W prime is also perpendicular to all x. This means that W prime minus W is perpendicular to all x, right. Now, how do we conclude from here that W is equal to W prime?
Choose x equals to W prime minus W.
Choose x appropriately, we just have to choose x. So observe, W minus W prime is now an element of W, right, it is actually on the subspace W itself. So we are allowed to choose x to be that element. Therefore you conclude that the norm square of W prime minus W is 0, which of course means that by positive definiteness that W prime minus W is 0. In other words, W prime equals W. Okay. So this is just sort of proof of uniqueness. So what this really shows is, and let me emphasize, the key point is the ambient space we do not care about, it can be infinite dimensional, you can be sitting inside some infinite dimensional space, but it is still perfectly well defined to project onto a finite dimensional subspace. Okay, and this sort of thing is actually very, very useful and important. So you mentioned Fourier series, for example, for example you may be talking about function spaces, that is where this actually really becomes useful. We wrote out this vector space yesterday, infinite dimensional space of all continuous, so let me call this C01, which is continuous real valued functions on 01, right. So this is all f, let me say real valued, I could similarly do complex also. So I take continuous real valued functions on 01, it is an infinite dimensional space, there are lots of nice finite dimensional subspaces of this, right. What are some nice examples of finite dimensional subspaces? Polynomial spaces, absolutely. So, you can say, okay, let me take all polynomials of degree at most 10, right. So, that is a 11 dimensional space, right. I can have 1 x square till x power 10, those are my basis vectors, for instance. So, I have got nice finite dimensional subspaces, and in a sense I can now ask, if I take an arbitrary polynomial f, can I project it onto this finite dimensional subspace that I am talking about, right. I want polynomials of degree at most 10. So, then the question is something like the following. I want so imagine I have this full set of polynomials, sorry, full set of continuous functions, and then there is this 10 dimensional subspace here of polynomials of degree at most 10 or 11 dimensional subspace. I am saying, okay, here is my arbitrary vector f, right. So, this is my space C01, this is polynomials degree less than or equal to 10. So, this orthogonal projection sort of allows you to replace or find, for a given polynomial f, I can find some, for a given continuous function f, I can find a polynomial f bar, okay, whose degree is at most 10, such that, what was the other thing that we talked about yesterday, that this orthogonal projection is also the solution to another optimization problem, which is finding the closest point, right. So, this orthogonal projection would actually be among all polynomials of degree at most 10, it is the guy whose norm, right, distance between f and f bar is the smallest possible. So, this is what you might call, this is the closest approximation or best approximation. Take a random continuous function, how will you approximate it by a polynomial in the best possible way? Answer is just do orthogonal projection, right. That is the best, there cannot be anything better, where you measure closeness by the usual norm, okay. So, among all polynomials of degree at most 10, this guy has the smallest norm. So, let us write that out also, we will come back to that in a minute. Okay. So, that is the reason why this general setting in which I phrased it, where V is an arbitrary space, could be infinite dimensional, but W is finite dimensional, this setting actually has applications, okay. So, we should not always live within finite dimensional settings, okay. So, that is just a remark there. Okay. So, let us slightly rephrase the theorem. So, to rephrase it a little bit, it is good to have a definition. So, this is called perp. So, let me say W is a subspace of V, V is an inner product space, and for this definition W can be any subspace, possibly even infinite dimensional. So, W perp by definition is just all vectors that are perpendicular to everything in W, it is all V in V such that V is perpendicular to x for all x in W. In other words, it is all V whose inner product with x is 0. Okay, so, we have defined a set, and this comes from the theorem in some sense, because theorem says you can find a W such that V minus W is perpendicular to everything on W. So, that sort of naturally leads to this definition. So, the key thing about this, very easy to check fact, is that W prime is also a subspace. Okay. So, if I start with the subspace and define its perp, the perp will also be a subspace. Okay. What it means is it should be closed under addition and scalar multiplication, and that is very easy to check. If I replace V by V1 plus V2, it will still satisfy this property. If I replace V by a scalar multiple of V, it will still satisfy the same property, right. So, checking it is a subspace is easy, but in fact something more interesting happens. This subspace has absolutely no intersection with W. So, in general, if I take I mean this is maybe intuitively clear from our usual ways of thinking about things in R3 and so on. See, if I am in R3 and my subspace W is a plane, W perp is just everything perpendicular to it, which means it is the normal to that plane, right. So this is our standard picture. Or if you are in R2 and say W is this line, W perp will just be the perpendicular line, right. So in all these cases it is kind of clear that W and W perp can't really intersect, they are kind of orthogonal to each other, right, they only intersect at the origin. But here we are saying this in a slightly more abstract setting. Just take any inner product space, for any inner product you define W perp in this way, then W and W perp are two subspaces which cannot intersect except at the origin. Okay. So let us just prove this second statement. If I have a vector which is in both of them, then let us just consider the inner product of V with itself. So this V here I will think of as an element of W, okay, and this V here I will, or maybe this V we will think of as an element of W perp, this V I will think of as an element of W. Okay, W belongs to both subspaces, so I can think of this fellow as coming from W perp, that fellow is coming from W. And what is the definition of W perp? It is everything which is perpendicular, right. So it has to be 0. So it just means VV is 0, therefore norm V square is 0, by positive definiteness of the inner product V has to be 0, right. So that is basically the proof here. Okay, any questions on any of this? So this is the picture we want to keep in mind. These are the sorts of things you get when you look at W and W perp. It is sort of the orthogonal, sometimes called the orthogonal complement of W. Okay. So now I am just going to go back to my theorem and restate it in terms of this new definition. So there exists a unique W such that V minus W is perpendicular to X, just means this V minus W, i.e. so let me just modify this, V minus W belongs to W perp. So that is what I am saying. Okay. So let us restate it again, slightly different form. So theorem again restated. So I will take the same hypothesis, V inner product space, W finite dimensional subspace, then given any vector V, there exists unique elements W in W and Z in W perp such that V equals W plus Z. Okay, so I just wrote it slightly differently. I just said I can now find two elements, one of them from W, another from W perp, such that V itself can be written as a sum of these two elements. Okay, so it is just a slight restatement. What should we, how should we prove this restated version from the original version? What should I take Z to be? Just take V minus W, that is all, right. So this theorem is not any different from the original theorem. All we are doing is saying in the original theorem given V I was able to, it said I can find a unique W, right. Take that W. Now to prove this restated version I should also construct a Z somehow, but the Z I kind of know what that Z has to be because Z is supposed to satisfy this equation, right. So choose Z to just be V minus W. Sorry sir, V in V, absolutely right, yes, thank you. Yes, given any V in V you can find W in W and Z in W perp. Okay, so now we know that from the original theorem V minus W is an element of W perp, that was the point of the original theorem. Okay, so we have kind of proved the restated version. Given a V, it somehow defines two elements which are now this element W and this element Z. Okay. So, it is the same theorem really, but it is sometimes useful, it is psychologically different from the original theorem. See, the original theorem says I have a subspace W, given a V I am only finding one element somehow, I am finding an element in W which sort of best approximates it, right, which is the orthogonal projection. Here given a V I am actually manufacturing two elements, right, psychologically I am thinking of it like that, there is an element from W and an element from its perpendicular, right. So, this is V, there is an element of W and an element of perpendicular. So, you are sort of saying I know the hypotenuse, and I can from the hypotenuse I can sort of find the other two sides, right, because I am requiring that it belongs to the subspace W. Okay, so that is just a restatement as I said before. Now this particular setting, this particular thing that I just now did is a very common construct, and this is what is called direct sums. So, let us just write this out. So, there is a slightly more general notion called a direct sum, okay, and all of this fits into that. So, direct sum is the following. So, let V be a vector space and W1, W2 be subspaces. Such that for every V in V I can find elements W1 and W2 such that V is W1 plus W2. What? No, at the moment I do not want inner product space. So, I am just saying in an abstract vector space I can still define a notion, okay, of direct sums, and when I now take inner product space I my whatever I have said until now will fit into that framework, but for this definition I do not need inner products. It is just a purely algebraic statement about I am only going to use the addition and scalar multiplication operations. Okay, so, if I have two subspaces with the property that any vector in the ambient space can be written as a sum of two vectors, one coming from this subspace, another coming from that subspace. If that happens, then we write, okay, if this happens, okay, if this happens, we write, so we say that V is the sum of these two subspaces. So, this is usually used, we say V is W1 plus W2, okay, this notation, this is just notation, just saying if I write V as W1 plus W2 I just mean that any vector in V can be decomposed like this, possibly in many different ways. Okay, so what are examples? For instance, I could take my vector space is R3 if you wish, and I can take W1 to be let us say xy plane, W2 to be the yz plane. Okay, what does xy plane mean? It is all vectors of the form x, y, 0, right, the z component is 0. Likewise, yz plane means okay. So, here are two subspaces. So, what are the dimensions of these spaces? 2, right, each of them is a 2-dimensional space. The ambient is a 3-dimensional space. Okay. I claim that the ambient space is actually a sum of these two subspaces. Why? If I give you any element of V, I can write it as an element from W1 and an element in W2, right. So, I mean in maybe multiple ways. So, for example, if I give you an element x, y, z in V, you could split it up as x, y, 0 plus 0, 0, z, right. Now, observe 0, 0, z is of course in the yz plane, because this x component is 0, that is all I want. Similarly, z component is 0 means it is in the xy plane. Alright, I have written it like this. Are there other ways of writing it?
X, y by 2, 0, y by 2, 0, y.
I could do x 0 0, 0 y z. That is another way of doing it. Any other ways?
Y by 2.
Half of them is
Half of what?
X, y by 2, 0.
Ah, okay, x y by 2 0,
0, y by 2.
0 y by 2 z, and so on. So, there are sort of, you can already see there are infinitely many ways of doing it in this case, right. I can tweak it many ways. So, here what it is really saying is that I should have at least one way of writing any vector as a sum of vectors like this, that is all. Often there will be infinitely many ways of doing it. So, if this happens, we say it is a sum. Okay. Now, there is an extra thing. Suppose in addition, okay, if every vector can be uniquely written like this, if every v has a unique expression as W1 plus W2. Okay. Then we write, then we say not just is V a sum, so if it has one, at least one expression, we say sum, but if it has only one expression, unique expression, then we say it is a direct sum. Okay. So, we just put that additional circle on top of this and we say V is the direct sum of these two subspaces. Okay. So, what is an example where you have a unique expression? So, let us say same thing as before, if I take r cube, I take W1 to be xy plane, W2 z axis. So, okay, I do not take a 2-dimensional space, but just a single 1-dimensional guy, the z axis. Then of course, it is clear that any x y z can only be decomposed in one way, it is x y 0 plus 0 0 z, right. So, this is in the z axis, this is in the xy plane, and there is really no other way of doing it. So, in this case r cubed is actually a direct sum of these two spaces. Okay. So, here is the interesting thing, it is actually very easy to figure out when you will have a unique expression. Okay. Is any guesses on when that would happen? So, let me just say what should be 0? Okay. So, you suppose V is a sum, then V is the direct sum if and only if the intersection is 0. Okay. So, suppose it is the sum of two subspaces, then this extra fact that there should be a unique expression is equivalent to saying that these two subspaces really do not intersect except at the origin. Okay. So, this again is not too hard to prove, maybe we will just prove this very quickly. So, if I have, so okay, let us just prove this, try to give the formal argument here. So, let us assume, let us prove the forward direction. So, let us assume that V is known to be the direct sum. So, everything has a unique expression. From that we have to show that W1 intersection W2 is just 0. So, let us pick an element. So, let Z be an element in the intersection. Now, this element actually has two expressions as you know a sum of W1 and W2, right. I can write it as either as Z plus 0 or 0 plus Z, but I know that there is a unique expression. I am given that it is a direct sum, but there exists a unique such expression which implies that this must be the same as this and this must be the same as this. Okay. So, that is the proof of one direction, the other direction is sort of easy. So, let me leave the other direction for you guys. Okay. So, that is the general notion of direct sum. So, why is this relevant to what we were doing? Because this sort of allows us to further restate what we were doing. So, back to our theorem, on orthogonal projections, the restated theorem, let us see what it said. Here is the restated theorem. It says given any V in V, there is a unique W in W and Z in W perp such that V can be written as a sum. So, what does this now translate to in the language of direct sums? V is the direct sum of W and. So, it says that these two subspaces W and W perp have the property that V is actually the direct sum of those two subspaces. So, it is now a very concise final expression. It says given any subspace W, there is another subspace W perp with the property that firstly every vector can be written as a sum of something from W and something from W perp, and there is a unique such way of doing it. Okay. And recall the uniqueness we also showed in the other manner, right? We also showed W intersection W perp is also 0. So, you can sort of, uniqueness was part of the theorem also, it was proved like that, but we can also see it from this other statement that W and W perp of course have 0 intersection. So, it must be unique if it exists. So, the key point is really the fact that it is a sum, everything has such a decomposition, that is a key here. Okay. And again all of this is, like I said, V can be infinite dimensional, we do not care, potentially infinite dimensional, but W must be finite dimensional. Okay, that is the setting in which we prove it. Okay, and so let us just quickly see the standard examples. So, if I take V to be, so examples, if I take V to be R cubed, W1 to be the xy plane, and what is W1 perp? It is exactly the Z axis, right. We can just actually compute the inner product. So, let us do another one. If V is R cubed and let us say W is the line spanned by the vector 1 1 1. Okay, now what is W perp in this case? Okay, it is a set of all x y z in R3, right, plane whose normal is this vector 1 1 1, right, and that is given by this equation x plus y. We can just take inner product. See, how do we get this? It is all x y z in R3 such that x y z inner product 1 1 1, see the dot product of this with 1 1 1 should be 0. But dot product is just x into 1 plus y into 1 plus z into 1. So, it is just x plus y plus z. So, that is just the equation of the plane, right. So, this is the usual thing that one does in 3-dimensional geometry and so on. The equation of the plane, how do you find the normal to a plane? You sort of just read off those coefficients, right. So, if I have a plane, for example 2x plus y plus 3z is 0. Okay, so, this some plane in R3, question is what is the normal vector to that plane? So, we just read the 3 coefficients off, right. So, we say the normal vector is 2 comma 1 comma 3, this is the normal vector, right. So, why is that? Well, you can sort of see that this plane is exactly the set of all x y z which is perpendicular to this one vector, right, just by the dot product. So, it is exactly that dot product with this vector is so the dot product of 2 1 3 with x y z being 0, this condition is exactly the same as this condition. Okay, so the plane is exactly all those vectors which are perpendicular to this line. So the line is normal to the plane also. Okay, so that's one thing. Now here is another little statement, lemma maybe. So if V is a finite dimensional in product space and W is a subspace of V, then if I take the perp of W, that is again a finite dimensional space. See, in general, if V is infinite dimensional and the finite a subspace is finite dimensional, the perp is typically going to be infinite dimensional, right. But if the ambient itself is finite dimensional, then subspace is finite dimensional, perp is also finite dimensional. Okay, so the claim is the perp of the perp is actually the original. Okay, so if you sort of take the perp of the perp, then what you will just get will be the original space. Okay, so this may be something we will take up in the tutorial. It is not going to be very important in what I am going to say next, but it is sort of intuitive, right. If I have a space, so here for example, here is my subspace, the normal is exactly W perp. If you call this as W, the normal, the space, the line is W perp. But if you choose your normal as your space W, then its perp is the plane itself, right. So W perp will just give you back the origin. Okay, so just say proof later or exercise. So this just says it behaves as you expect. Okay, so all of this is fine, and so now this brings us to sort of the important definition or the important part of this whole thing. See, all along again we go back to our original theorem. It says that the theorem on orthogonal projection, given a subspace W and a vector, I can always find this W, right, this projection. Now let us do the following, let us define a map which associates to each V the corresponding W. Okay, so let us define a map now. So it is a map from V to V if you wish, let us call it P. What does it do? Take any vector V and you map it to the corresponding W, okay, where W is, what is that W? It is the W which occurs in the theorem. It is that unique W such that V minus W is perpendicular to this, okay. Or you can say it in terms of this earlier theorem, that you write V as W plus Z, and what I am saying is I take a V and I map it to the corresponding W. So I take this V and I map it to just this first component to W. So this is my map. Okay. So I define a map like this, and this map, so here is the sort of theorem, define a map from V to V like this. Theorem says firstly that P is linear. Correct. I mean I can always say it is V to V. However, like you say, the range will only be W, correct, but I want to think of it as an operator on V, map from V to V. So the point is P is linear, it is a linear operator. Okay, so that's already not very clear, because the way we defined the orthogonal projection was say, okay, I take this and then there is some formula which tells me how to find the W. The thing we have to check is that if I vary V linearly, if I take V1 plus V2, then the formula should be such that W1 plus W2 is what I should get as my answer, right. So it's a question of checking that the way we constructed this W is a linear function, it sort of varies linearly with respect to V. So that is the first statement here. So here is the second statement which addresses your concern, the range is only W, okay, and the null space is actually W perp. okay, and statement 3 says if I compose P with itself I get back P, okay, P squared is P. So, these are sort of the 3 important statements, and further if V itself is finite dimensional, so I can also talk about W perp. So, if then you know the okay, let me not do this now, I will come back to this. So, here are 3 statements. This map which associates V to W is firstly linear, its range is P and the range is W and null space is W perp, and thirdly that P is what is called idempotent, P squared is P. Okay. So, let us just prove each of these statements. So, the first statement says it is linear. So, what was the definition of P? So, here is how we define P, recall. I had to choose an orthonormal basis, right. First take S to be EI orthonormal basis, then my definition of W was P EI EI. This is how I think of my what my W is, correct. So, this is my definition of P. Now, the question is, does it vary linearly with respect to V? So, if I now write, if I take V1 plus V2 or more generally any multiple alpha 1 V1 plus alpha 2 V2, right, alpha 1 alpha 2 are scalars, if I take this and try to apply my formula, will it somehow split linearly is the question. Okay, and now this is just a property of the inner product, that when I in the first component if I change things linearly it just comes out, right, the scalars come out. So, I can write it as alpha 1 V1 EI EI plus and it is a sum over all EI, and that is exactly alpha 1 P V1 plus alpha 2 P V2. So, it is linear with respect to V. So, firstly it is a linear operator. So, that is the first statement. The second statement said something about the range and the null space. So, let us check that. So, firstly range of P, one thing we know for sure is that it is going to be a subset of W, right, because that is by definition more or less that P of anything is an element of W. So, that is all right, but why is it equal to W is the question.
The position of W is W itself.
Okay. So, the observation here is that if you project a vector that is not in W to W, you know, something like this happens, but if you are actually in W to begin with, if my vector itself were in W, the projection does nothing to it, right, it just sends it back to itself. Okay. And how do we see that? Well, we can just see that from the definition here. So, observe that if W is in W, then what does that mean? W is a linear combination of the EIs, right. We already know what linear combination it is. This is how you figure out the coefficients in the linear combination. It is a linear combination with these as the coefficients, but then this is exactly the definition of PW. This is how we define the projection, right. So, I mean this is again intuitive, right, when you project onto a subspace, if you are already on the subspace there is nothing to do. Okay. So, what this says is that if I take P and I restrict P to W, it is just the identity map. The restriction of P to the subspace is just the identity map on the subspace. Okay. So, that tells you in particular that every element of W is surely in the range of P, because take an element of W that occurs as P of itself, right. So, therefore, it tells us quite a few things. So, observe firstly that therefore, W in W means W can be written as P of itself, therefore, it belongs to the range. So, we have also shown the other way around, and so W is also in the range. Okay. but actually we have also shown part 3 that we needed to show. So what did we have to show? So this is the key thing that one has to keep in mind. I claim that this actually tells us that p squared is p. Okay, why? Because p squared just means you apply p twice, right. So if I apply p to any vector v, the answer is already in W now. This is come inside W, and so if I add p on it again, then it will not change it. Right. On W, p acts as identity. So on W, this will just give me back the same answer. Is all right. So this just this property here, p when it acts on an element of W will give back the same guy. That is what this property says. So in particular, I first act p so that my vector falls inside W, then I act p again, it does nothing to it. So I get back the PV itself. Is okay. So this just says p square is p. So we have shown the third thing that we needed to show. The only thing that's left to show is the null space is W per. Okay. So let us compute the null space. So what is the null space of this map P? Just means it is all those vectors such that PV is 0. Okay. We could for example just use the definition PV 0 just means V EI is 0, right. Therefore it means that all the VEIs are 0. So this just means that. Therefore V is perpendicular to all the EIs, in particular it is perpendicular to all vectors. In EIs are a basis. So if it is perpendicular to EIs, it is also perpendicular. In other words, it belongs to W per. So the null space is definitely contained in W per. Okay. The other way around is very easy. If I take something, the same proof if you wish, something is in W per, you just apply the definition of P and you see that you will get 0 as the answer. Okay. So this is actually easy. Okay. So this guy is maybe the single most important, even though it does not quite look like it, it is maybe the most important notion in this whole business. So this operator P is called the orthogonal projection of V onto W. Okay. So it's a linear operator, and in a sense, see it's a slightly different point of view if you wish. So there are two different ways of thinking about an inner product space and subspaces of an inner product space. On the one hand, so here's maybe one point of view, you could just choose to live inside the world of subspaces. So you'll say, okay, here's all subspaces of my inner product space. Now that's some collection of all possible subspaces, either infinitely many of them. And on the other hand, there are these various operators P. So this left hand side is you're living in the world of vector spaces and vector subspaces. On the right hand side, we are going to live in the world of operators. So this is a collection of certain operators on V. Okay, what operators? So what am I saying? Here's a translation. To each W, I can associate its corresponding orthogonal projection. Okay, so either you study subspaces in the language of subspaces, or you study these special kinds of operators, which are these orthogonal projections. Okay, and what does it mean for, what are the special properties of P? How do I characterize an orthogonal projection? Well, we've seen some properties. P square is P, for example. So why is this a special sort of operator? It's an idempotent operator. It's got this property that P square equals P. Okay, so we will come back to this just a minute. So to actually place this in correct context, let me just make this slightly more general. So again, we are going to talk about general vector spaces. So before I do that, any questions on what an orthogonal projection operator is? Is everything all right? Okay. So, see, these projection operators can be defined in more generality. Okay, I do not need inner product spaces. Let us imagine I do not have an inner product, I have just got a abstract vector space, that is all. Now, if I have a vector space and suppose I have two subspaces. So, here is my given starting data. Okay, I am given a vector space V and I am given two subspaces W1, W2 subspaces of V such that V is W1 direct sum W2. So, I give you two subspaces such that V is their direct sum. Sometimes we call these as complementary subspaces. So, what is the example that we have in mind secretly that we will eventually apply this to? It is the case when V is an inner product space and W1 is some subspace and W2 is the perp of that subspace. So, this is the example that we eventually want to keep in mind, but that is something which only works when you have an inner product, right? Only then I can talk about perp. What if I do not have inner products? What if I have just a abstract vector space with only this vector space structure, addition and scalar multiplication? Then what I can do is I want a pair of subspaces W1 and W2 whose direct sum is V. Suppose I have such a pair, then I can still define some analog of this projection. Okay, how do we do it? Let's see what does it mean for V to be a direct sum. This just means given any vector V, we know that there exists unique elements W1 and W2 in these two spaces. So, given V, there is a unique W1 and W2 such that V can be written in this way, right. So, let me use the same thing that we did earlier to define a projection operator. Okay. So, let us now do the same thing. Let us define, maybe we should call this something else or still P, I am not sure, maybe we will call it P again. So, let me define a projection operator P from V to V as follows. For any vector V, I will just associate, sorry, is there a question? Okay, maybe not. So, if I have a general vector V, I will define an operator like this. I will just map V to that first component W1, right. This is something I can always do because I know that V has unique such representation. I take that unique representation and just keep track of the first component alone. So, that is my map. Okay. Now, let us see what properties this map will have. Observe again, firstly P will actually be linear. Yes, I claim P has the following properties. It is linear, its range is W1, its null space is W2, thirdly that P square is P. So, it has more or less the same properties that we had earlier, except now range is W1, null space is W2. I need both of them to be given to me in order to define this map. That is the only thing. Earlier I did not need that. When I have an inner product space, if you gave me W, the complementary guy that I chose was just its perp. So, if I know W, I automatically know W perp. Here it is not like that. You have to tell me what is W1, you must tell me what is W2 also. Okay. So, let us just check these, that it actually works in this generality. Why is P linear, for example? So, let us do this. So, let us prove property 1. So, suppose I have a sum of two vectors. So, V, let us say V1 and V2. Okay, so, V1 has been written as W1, that seems, maybe I should not call it V1, let us call it V. Suppose I have a vector V which is W1 plus W2 and another vector V prime which is W1 prime plus W2 prime. Okay, I decompose it like this. Now, let me calculate what is P of V1, what is P of V plus V prime. So, to calculate P of V plus V prime, what am I required to do? I am required to take this vector V plus V prime and find out what is its decomposition as an element of W1 plus an element of W2, right. But I know one candidate decomposition, which is just add these two equations. One way of writing it I can figure out how. I just add these two equations. So, it is W1 plus W1 prime, that is definitely an element of W1. W2 plus W2 prime is definitely an element of W2, right. So, alright, I just added the two equations, but why does that tell me that P of V plus V prime is this guy? By uniqueness. There is really only one unique way of doing it. So, if you find one way of doing it, that is your way, that is all, you are sure that that is the only option. So, this is actually W1 plus W1 prime, sort of by uniqueness if you wish. Okay. So, that is what we need to prove. This is PV plus PV prime. Likewise, you prove the scalar multiplication as well. Okay. Okay. Now, let us sort of show the other thing. Let us show the thing that is most important, that P, when you restrict to W1, it will just be the identity on W1. This is the key point that we need to show. Okay, that will actually imply P square is P like before and so on. So, what is P when you restrict to W1? So, if I take an element of, if V is in W1, I claim that PV is P itself, PV is V itself, right. Why is this true? There is only one way of writing V, right. V, I have to figure out how to write it as a sum, but there is only one way, which is V1 plus 0, V plus 0. Therefore, PV had better be this guy, right. So, that just tells me that on W1 it is the identity, therefore, same logic as before, if I apply P twice. So, observe that when I apply P once, the answer is definitely going to be in W1, and so when I apply P twice to something, the first time I apply it, it falls inside W1, the second time I apply it, P does nothing to it, P keeps it as identity, P acts like identity on it, right. So, P square V is PV again, so it just tells me P square is P, okay. And so, the rest of the, I mean statement 2 is easy. So, range P I have already shown its subset of W1, but by the same logic that we used earlier, it is actually equal to W1, and similarly you can show that null space of P is W2. Okay, so, I am just going to leave that last bits as exercise. So, what we have actually succeeded in doing here is in figuring out the most general context in which projections make sense. Okay. So, projection does not actually require an inner product space. If you have a vector space and two complementary subspaces, something whose direct sum is the whole, then you can again define a projection like this. Okay. So, in this case, this operator P is called the projection of V onto W1. That by itself is not complete information, because for the same W1 I could have many different W2s, right, many different complementary subspaces. So, you somehow need your English sentence to also somehow bring W2 into the picture. So, we usually say along W2. So, it is the projection of V onto W1 along W2, and this just has a simple meaning in terms of vectors that one is used to. So, imagine in R2 this is your W1, this space here is your W1, and this one dimensional space line spanned by this is W2, okay, and they are at some angle to each other. So, I have got two one dimensional spaces, and now I am going to geometrically try to understand what does this projection mean. So, if we give you some vector V, I want to figure out what is P of V, what is projection of V onto W1 along W2 mean. So, the answer is
the parallel line
right.
through
Okay.
along
Okay. So, what I have to do is decompose this vector as a sum of two vectors, right. I must write it as the sum of W1 and W2, two vectors in these two spaces. So how will I do this? Well, we just do this usual parallelogram law, right? Parallelogram rule. So what I do is I draw through P, I draw a line parallel to W2. Through this V, I draw another guy which is parallel to this, and where it meets, this fellow is my W1 and this fellow is my W2, right. Their sum is exactly V by the parallelogram law for vector addition, right, and by construction W1 is in W1 and W2 is in W2. So I've correctly figured out how to draw it so that their sum adds up to V, and this fellow is in W1, that fellow is in W2, right. So this is what the projection now means. So what is a projection? It is just a map which associates, it takes this V to this fellow W1, right. So how do I get that projection? I start with V and I sort of go along W2, matlab parallel to W2, right. So I start here and I sort of move parallel to W2 till I hit W1 somewhere, the space W1. So that is where the word along comes. So you project, but you sort of have to project along W2. Now if I change W2, the whole thing will change, the projection will change, right. So if this is my W1 and maybe my W2 is this, then the way I get my projection is I am going to have to take this vector V and now start here and draw a line parallel to W2, and where it meets, that is my W1. So if this is my V, this is my W1 in this case, right. In this case it is something else. So the answer, the projection very much uses both pieces of information. I need W1, I also need to know what is W2, only then my projection is well defined, okay. Okay, so this is the general notion of projections, and so this is sort of what I meant by saying there is, you can either work with pairs of subspaces, pairs of complementary subspaces, or with idempotent operators, okay. So let me just try to make this, I mean this is a good point of view to keep in mind. So in this general context of vector spaces, so let me just assume V is a finite dimensional vector space here, okay, maybe I do not need it for everything I am about to say, but it is alright, let us just assume V is finite dimensional, and conceptually on the one hand we want to collect together all possible ways of writing V as a direct sum of two subspaces, okay. So let me call this collection as D, the set of all direct sums. It is all pairs W1, W2 of subspaces such that V is actually the direct sum of those two fellows, okay. So for example in what I said earlier, I can take this and this as my W1 and W2, this and this, or this and this, or any pair of non-parallel lines essentially, right. All of these are, if you wish, in R2 these are all collections of these are all pairs W1, W2 whose direct sum is the whole space, right. So I have many such collections. In fact I also have one trivial thing, I can take one of them to be the 0 space, the other to be all of R2 also. That's, I mean W1 can be 0, W2 can be the whole space, that is also a direct sum. So I have many direct sums, right. So there is this huge zoo of possibilities, and what I am saying is let me conceptually just collect all of them together, think of all pairs of subspaces whose direct sum is the whole thing, that is one collection. The other thing is, it is maybe slightly more tractable, this is the set of, let me call it the set I will just denote the set of all linear operators, okay, linear transformation such that P square is P. So I for idempotent, so I am on the other hand I am saying let me take the set of collection of all idempotent operators, okay. So if you think in terms of matrices, for example, if V is some finite dimensional space, what is my I is just all n cross n matrices A such that A square equals A. I will fix some basis, I will write my operator in that basis, then the collection that I am thinking of as I is just all matrices whose square is itself, that is all. So it is actually much more tractable than my D, right. My D is some crazy collection of all subspaces which are complementary. This is just all matrices whose square is itself, but these two are actually the same thing. Okay. So everything that we have said until now finally culminates in this following concise summary. It says that D and I are actually the same sets. There is this nice bijection between D and I. You conceptually should think of them as being the exact same object. Okay. And what is the bijection? So theorem, there exists a bijection between these two sets defined as follows. And what is the bijection? I take a pair W1 W2, and to that pair I will just associate that map P which I the projection onto W1 along W2. That is how I think of this pair as a projection, just as an idempotent operator. Conversely, if I give you an idempotent operator T, okay, T is now an idempotent operator. How do I construct my W1 and W2? Take the range space and null space. Okay. So an idempotent operator has a range space and a null space, and that pair I claim will always be a direct sum. Okay. So this forward direction we just looked at, let's just analyze the reverse direction for a little bit. So I am claiming that if T is an idempotent operator, then the range space of T direct sum the null space of T is actually the whole vector space. I mean V is actually the direct sum of these two guys. Okay. So let us check. How do I show this? I have to show that any vector V in V can be written as an element of the range space plus an element of the null space, right. Firstly, I should have at least one way of doing it, something from range space, something from null space. What is the decomposition? How do I do this? What?
PV plus minus T.
So here's one thing you can do. You want something in the range of T. So let's actually just apply T to V. That's guaranteed to be in the range. Okay. So we've got something, but to make this equation correct, you have to apply. You must subtract it out. So I claim. So this is in the range is easy, but claim is this is in the null space. Okay. So let us check that V minus TV is in the null space of T. So how do we check? You apply T to it and see what you get. Of course, T is idempotent, right. So TV is equal to square. So that is one way of writing it as a sum, but why is this unique? To show it is a direct sum, I have to show it is unique, right. Alternatively, what can I show? Intersection is 0. So that is the usefulness of that condition. It is not always easy to show uniqueness of an expression. See, by hook or crook you can manufacture one expression, which is what we have done here, but then to show that that is the only expression and so on is a pain sometimes. Instead we can just use the other characterization. It says that if you can show these two subspaces have no intersection, then surely it is a direct sum now. I mean it is a sum and the subspaces have no intersection. So let us show that the subspaces have no intersection. Suppose something is in the range and in the null space. So let us take an element x in the range space and null space. What does it mean? So x is the range space, I will write it as some ty, right, because it is in the range space. X is in the null space means Tx is 0. These are the two properties I know. Okay, now I just combine these two things. This means that T of Ty is 0, right, which means T square y is 0, but T square is T, but Ty is 0, so why is that good? Ty is x, right. So you just sort of have to chase the diagram a little bit, but finally we concluded that x is actually 0. So there is only one element, there is intersection which is just the 0. Okay, so what is all this good for? Finally, what we have done is to sort of just look at this very general setting in which we can talk about projections, that it is essentially idempotent operator, that is what a projection is. Okay. If you have an idempotent operator, you get a range and null space, and those two are your W1 and W2. You are projecting onto the range along the null space, that is what is always happening. Okay. Now all this is general, of course. Now the reason for launching into this detour is because we are interested in a special case, however, that is, what is it that we care about? The space V for us is not just a vector space, it is an inner product space. Let me even take finite dimensional inner product space. Okay. What? No, x is in the range, right? So I wrote x as ty because x comes from range.
So t of tx equal to.
No, the second equation is because x is in the null space. X is in the null space means tx is 0.
The next one.
T of ty. T of x is, I have replaced x by ty, that is all. Is alright? See, tx is 0, instead of x I have put ty. Is alright? So it is t of ty, no? Okay. Okay, now let us come to our interest. Our interest is not in, see, the space script D which I wrote, direct sums, right? It is all pairs W1, W2 of subspaces where V can be written as their direct sum. But that is not what we want. For us, we are only interested in orthogonal projections. So what does that mean? I am actually going to look at only certain special types of pairs. Okay, no W1 and W2 at some crazy angle to it, W2 should be perpendicular to W1. So I am going to take only pairs of a special form take a subspace W and take its perp. That pair, those pairs are what I care about because we are only going to look at orthogonal projections. So this of course is a sub of this D, right, because we know that if I take any W, W direct sum W perp will always be the whole space. That was our theorem. Okay, so now the question becomes the following: if you want to restrict yourself to this special pairs, what do you get on the other side? That is, remember I have my bijection here. So I said D and I are really the same fellows, right? But now if I take special elements of D, things of the form W, W perp, it stands to reason that what I am getting on the right hand side are not just random idempotents, they are idempotents which are special in some manner, right. So under this map I am actually getting some special idempotents. Okay. So the question is, in what way are they special? So under this bijection, see, D orth is actually a sub of D. D is isomorphic to I mean is bijective to I. So the question I am asking is, if I start with these sorts of pairs, what do I get? Right? What are these? How are these projections special? Okay. So under this bijection, let us call this bijection something. Suppose I have a bijection psi. I am asking what is the image of D orth under psi? Right? Which subset of idempotents do you get? Okay. So let me just phrase the question for now. We will come back to this question later on. So just keep this somewhere in the back of your mind. Question is, in what way are orthogonal projections Okay, so remember these sorts of P's are what you call orthogonal projections onto subspaces. In what way are orthogonal projections onto subspaces special? How are they special? In the class of all idempotents. Okay. So, I hope my question is clear. I am not going to answer it right now. So, we will come back to this question later on once we have talked about adjoints of operators and so on. Okay. But for now, at least I hope I have convinced you that you started out with the case we were interested in of orthogonal projections, then we sort of enlarged it to this larger class of all possible projections of along onto W1 along W2. But then now we are coming back, so we went there and we realized that that class is actually just a set of all idempotent matrices, and now we want to come back and answer the question, suppose you had an orthogonal projection, it should correspond to some special kind of idempotent, right. So what are those special idempotents? Okay. So we will answer this question later on. So it involves the notion of adjoints of operators. Okay. So any questions so far? So it's I realize a lot of this is slightly more abstract than necessary maybe, but I think having this broader picture in mind sometimes makes it much easier to analyze various situations of projections that you may be wanting to do. Any questions from the online audience?
So do we really have to see the psi as from D itself? What we need is
Psi on D orth. Sorry, ask your question.
Is there any perspective to see psi is a map from D to I instead of D or?
Is there any?
Yeah. Like why do we have to look at what we are interested in looking at the psi or looking at the projection from which is actually erased from the orthogonal.
Right. So this is after all the only case we care about. Why enlarge this thing? No, I guess the answer is on one hand because this works even in the absence of inner products. So the natural question is this, right? We have a notion of orthogonal projection, but what if we are going to be working in spaces without any natural inner product in play? We may still want to do projections. See, projections are sort of like saying, okay, I have a vector in my ambient space, I have some subspace which is of interest, which is controllable by me, and then I want to say, okay, can I take this fellow and somehow map it onto some best possible element of the subspace, right? That's sort of broadly what projection is trying to do, right? Now the thing is, suppose there are no inner products in play, but I still have the same kind of situation, some ambient vector space and some controlled subspace which I can somehow understand better, and I am interested in saying, okay, I have an arbitrary vector, I somehow want to, the original vector is too complicated to understand, I want to somehow map it down to my controlled subspace, right. In the absence of inner products, how would you formulate this problem? What does it even mean to map it down? That is what is given by this projection along the complementary subspace. So what it says is, okay, there is a controlled space, maybe there is some nicely controlled complement also. If you know some complementary subspace W2 which is natural in that application you have in mind, then you may say, okay, I will somehow try to take this vector, I will project out the W2 component and then project along that and go to W1 and see what I get. So it's not a good answer overall, it depends on what your application is, I think, at the end of the day. But the reason I wanted to go into this is because this is something which does not involve inner products. It could work even when there is no natural inner product in place, but the trade off is you will need to be able to figure out what your W2 is in order to do it. So there may well be applications where that works.
I see, like if you have two different camera angle, for example, then if you want to analyze a three-dimensional image, all that I get is the projections
along each of
them. So we may be able to recreate the three-dimensional object using these tools.
But that is maybe not an example of this, because there what you are doing is you have maybe two different subspaces. There is a W1 and then you are doing orthogonal projection onto W1.
Imagine I have a W1 plus W2. However, I know just the projection of V on W1 as well as projection of V on W2.
But projection is orthogonal projection, right? Not projection of V along this. See, yes. Projecting along this is the parallelogram wala business, right? This is what you should be doing if you are projecting along the complement. What you have in mind is maybe the following situation: I have one W1 and one W2, and there is something you are interested in. You know how to orthogonally project it onto this space and orthogonally project it onto that space. So then if you know that, you sort of want to maybe use that to recreate. But this is like doing two separate orthogonal projections. See, this is as if you don't have this, right? And you just have one guy and you know orthogonal projection. Now you repeat the same thing. You have only the other guy and you have orthogonal projection. So it's like two separate problems. W1 and W2 are not really, the fact that they are complements is not involved in your analysis. When would that be involved? Only when you are doing this sort of thing, when you are trying to go parallel to W2, you are going along W2 and reaching W1. That sort of thing when you are doing, there you are using this kind of complementation.
The same thing will not be there for the W2 along W1.
Yes, it is also there. Yes, I didn't say that. So let's do that now that we are here. So this projection actually comes in pairs. There is also a projection onto W2 along W1. Okay, so what is that projection, for example? Okay, it is just I minus P, right? See, if I write V as W1 plus W2, and my projection is just mapping V to W1, right? This is the projection of V onto W1 along W2. The other projection you have in mind, let's call it P prime. What is that supposed to do? It's supposed to map it to W2, the other component. So there is the other projection. That projection is just nothing but W minus W1, that's all. So what is W minus W1? It's just identity minus P acting on V. V, sorry sir, it is V minus W1. So which is identity minus P acting on V, right? So this projection, one of the projections is P, the other projection is I minus P, that's all, right? So there is a projection onto W1 along W2, which is P. There is a projection onto W2 along W1, which is I minus P, that's all. The sum of the two projections has to be identity, because that is equal to the original vector, right? So these two projections always come in pairs in some sense. There is a projection P and I minus that projection, which is the projection onto the complement. That is also true for orthogonal complements. So when I have, see, if I have two orthogonal subspaces, W and W perp, and I want to figure out what is projection. See, if I have W, I have W perp. That orthogonal projection we talked about, that is PV, for example, onto W. And if you want to know what is the opposite thing, say, I mean, what is the other guy, that is this much, right? That is just V minus PV. See, this is PV and V is just a sum of these two things, right? V is just PV plus V minus PV, that is my V. So the projection onto the subspace W perp is exactly V minus PV, which is identity minus P. So in a sense, projections also come in these pairs. You can think of them as P and I minus P. Okay, so okay, maybe I will just say one last thing and then we will pick this up from tomorrow. So orthogonal projections are special idempotents. That is a summary of this whole long discussion, and we will figure out in what way they are special. But returning back to our very first theorem, which is the definition of orthogonal projection, its importance comes from the second way of thinking about it, which is that it minimizes the it's a best approximation, it minimizes the norm, right. So recall that is the other important thing. The key property of the projection is the following. So if P is the orthogonal projection of V onto W. See, orthogonal projection of V onto W is also another way of saying it is it is the projection of V onto W along W perp. This is another way of saying the same thing, right, two different English sentences which mean the same thing. So the word orthogonal is really shorthand for this along W perp. We just put that orthogonal in front and that just tells us it means you are projecting along W perp, that is all. Okay, so the orthogonal projection has the following property. Then if I take V minus PV, this fellow is actually less than or equal to V minus X for all X and W, right. So this is the shortest or the closest approximation. That was the thing that we did last time. So that is the other property of this projection, that somehow V minus PV, which is same as I minus P. See, remember we just talked about it just now, I minus P is the other complementary projection. So what this is saying is if you take I minus P and I act it on V, the answer is less than or equal to V minus X for all X and W. So this is just another way of rewriting the same thing. So I have just used the projection operator P to restate what we stated last time on the best approximation. Okay, maybe this is a good place to start and to stop and pick up the thread from next time. So next time I will talk about this Gram-Schmidt. So all of everything that I said finally hinged on the definition of P at the very beginning, and the definition of P itself required that we should have an orthonormal base, right. This was my starting point. I said I need an orthonormal basis of W in order to even define my P cleverly, and so that is the first thing we will fix next time. Why does an orthonormal basis exist in general, the algorithm itself, which I am sure you have seen before, but more interestingly what are the various variants of that algorithm, how we can use the same algorithm to sort of solve other computational problems, what are the main strength of that algorithm in actual in actual computations, things like that. Okay, we will stop here. So I have already uploaded the assignment sheet for today onto that Google Drive, okay, sent email also.
Hello, sir.
Yeah.
Yeah, I have sir one question. I already wrote in the comments that if we start some infinite dimensional space V,
Yeah.
why it is necessary that that subspace should be that W subspace should be finite dimension?
No, that is just for the definition of the projection itself. So I am just defining my orthogonal projection by starting with some finite orthonormal basis for V. See, if my space W is infinite dimensional, then it is not clear to me I will have a finite orthonormal basis, right. I mean I will not have it, and then my definition will not work. If it is an infinite, if S is an infinite set, then this thing that is written here will be an infinite sum, and that will not make sense. So that is maybe one reason why I need a finite dimensional space. And like I said, in general you can actually make this work, but then you will need to impose some additional. So the typical setting in which this is proved is you have a Hilbert space and then you have a finite closed subspace and so on. So
that means in general it is not mandatory that W must be of finite dimension.
It is not mandatory, but then you must impose some other condition on W. If you do not have finite dimensionality, you need this thing of closedness inside a Hilbert space, etc. So some other conditions are required.
And sir, one more thing. So to define perp of W perp, we considered that V must be, you wrote that U is some finite dimension space.
Correct, yes.
Then only you said that W perp of W perp is equal to W.
Yes, correct.
So if that means that in infinite dimensional space, we might have some example that perp of W perp need not be equal to W.
Correct, yeah, it can be, you can show one way inclusion easily, but the equality will require some dimension argument. So that is the reason why I wanted the ambient space to be finite. Yes, you are right, yes.